Yesterday, remember, we did the story of evolution, and we spoke about the fact that in a population of organisms that there was genetic variation. In other words, organisms are different from one another, even though they are from the same species. What was the relevance of that? These organisms live in changing environments, and as environments change, those organisms that are adapted to that environment survive, they are selected for, therefore they go forth and breed and pass their genes on to future generations, whereas we know that those organisms that are not adapted to the environment will not survive, therefore not breed, so they're selected against, and therefore their genes will not continue into the future generations. Now, we know that the story of evolution is ultimately linked to the story of fossils. Because how did we know what organism lived when and how did it live and how old is it and all the rest of it? By looking at the fossil records, which we're going to start looking at now. Okay. So the first thing I want to do before we go into any of our questions, I want us to look at the process of fossilization. So, basically we know that if an organism is going to become fossilized, it needs to have the right conditions for fossilization to occur. So if we come to this process here, there is our merry little dinosaur we can see from back in the day, walking on the top of the earth over there. Our dinosaur dies. We're not sure why he dies, but he passed on over there. And then, of course, we know that there must be good conditions to enable a fossil to actually form. So we want a few things. Number one, we want our fossil to become covered with sand. If it gets covered by layers of sand, and then, of course, water, either a river runs over it or maybe it rains, in the sand there are minerals. And what happens is that layers of sand, together with water running down with the minerals, does two things. The water running down with the minerals actually glues the soil particles together and then begins the formation of rock. And also, by having layers of sand, like if you look at this diagram, the third piece over here, we can see that there are a number of layers of sand on top of our fossil over there. There's water over there, so the water is going to be running through. The minerals are going to be seeping through or leaching through the sand, together with the layers of sand on top that are creating pressure, give rise to the formation of a fossil. And what we call sedimentary rock around that particular fossil. Now you can see, if you look over here, that our fossil has actually come, our fossil has actually come to the surface in that area over there. And very often what happens is that layers of, or fossils that are buried deep under the ground, there's earth movement or something like that, and some of the lower layers become sort of up, they spat up to the surface of the earth, which will sometimes therefore expose the fossil. So that is the process of fossilization. Always remember that not everything is able to fossilize. That's why things with skeletons, hard bodies, snails with shells, those kind of things tend to be the best things that create fossils. Generally, our soft-bodied organisms do not fossilize well at all.
Okay. So, David, also looking at fossils and stuff,
yes,
we know that the examples are also always given by bones and stuff, clearly because they're more tough or whatever.
Yes.
So I want to know, is it just bones that actually, or is it just things that you could have used? So if apes were living 10,000 years ago and they used a certain cup, or what, they don't have cups maybe, but whatever it is that they use, would that also be regarded as a fossil?
That's interesting, because when we look at other fossils, we've got our paleontologist who actually removes the fossil from the ground. Okay. We've got, that's the archaeologist who removes the fossil from the ground. Together with the archaeologist, we've got our geologist, who's looking at the rock formations and trying to determine the conditions of the earth at the time, and maybe how old the rock is potentially that fossil is found in. Then we get the paleontologist, who looks at the bones and determines, that relates back to the work that we were doing yesterday, whether we have homologous or analogous features. Homologous features means that the bones are the same, and we can look back and see these bones have similar features, and therefore we say that they would be related to each other. But coming back to what you say, an anthropologist would be looking at the digging site and see maybe there's a burial ritual or cups or tools or those kind of things. But generally, when we're talking about the anthropologist, we're talking about the evolution of human beings. Generally, anthropologists are not involved in other organisms other than human beings. Yeah. Okay. So, of course, we know that once our organism is fossilized, it is, if we want to try and plot a fossil record, we would need to know how old the organism is. So if we come to this question over here, it says, one way to determine the age of a fossil is to use the rate of decay of carbon-14. Now, what I just want to say here is that all elements are, in fact, radioactive. Even though we're not talking about massive radioactivity that could affect us, but they are radioactive and therefore are able to change. So something that does change is carbon. Carbon changes from carbon-14 to carbon-13 over a period of time. Okay? It's just a change in its radioactivity. And we know how long it takes for, if we've got a certain, for example, skeleton, we know how long it takes for a certain amount of carbon-14 to change to carbon-13. So if we look at a skeleton, and we can work out how much carbon-14 is there, how much carbon-13 is there, and we can determine the age of the actual skeleton at that time. So if we look at this over here, we're looking at our carbon-14. This, our x-axis over here, remember, which is our independent variable. We're looking at time per 10,000 years. And we are looking at, in relation to that time, the percentage of original carbon-14. And as we can see, if we follow the curve going down, that the further away, or the longer time has passed, the amount of carbon-14 goes further and further down, and therefore the amount of carbon-13 has gone up. That would mean your fossil is getting older and older and older. So if we look at some questions relating to this, it says, a fossil snail was found to have 30% of its carbon-14 remaining. According to the above graph, the age of the fossil is approximately. So it said that there was 30% of carbon-14. So I will use my resource over here. There is the percentage. Remember, be careful of your axes. There is the percentage over there. 30% is about there. And I can see it goes down to 1. So I would say that fossil is approximately 10,000 years old, because remember, 1 times 10,000, as we can see from that over there. But please remember that when we're dealing with carbon dating, that tends to be good for dating fossils. When we're trying to date rocks to maybe millions of years old, we will be using other elements in terms of our radioactive dating. Okay, right, it then says, some fossils are typical of a particular period on the Earth's history. Fossil organisms have lived only in that period, and it is then possible to determine the age of the rock in which these fossils are found. Some fossils are called index fossils. So that we found that in certain layers of rock or strata of the sedimentary rock, that we only find fossils in that particular time period. And then we know that if we find those fossils in another region, we will know we can link it to that particular time period. So a typical index fossil is the trilobite that lived in the oceans during the Paleozoic era. At the end of this era, they became extinct. So if the rock contains trilobites, we can conclude that the rock was found during that area. And here we look at 3 different strata. And basically, because we're going to run out of time, I'm just going to say that if you looked at this, I would see that that area there and that area there will be the same time period. They're 3 different areas in the Earth, but of course they will be different time periods. Again, if I look at this over here, area 5 and the other area, area 12, is the same time in the history of the Earth, because it's only got those index fossils found in that particular area.
Oh, all right.
Okay, we'll continue just now.
Yep.